Okay, this is the second lecture in Physics 313, the actual in-person Zoom recordings or in live Zoom recordings. And let's start with the PowerPoint slides. Again, so these are all things that we're expected to have read, that watch the video. These slides, if they haven't been already, they'll be posted to your Blackboard very soon. Some sections have them posted, some not. And this lecture is for all of my 313 sections, my specific ones. And it's going to be a quick review of these PowerPoints. So quick review, and then we'll do a couple of examples. So we did this quick check question about which of these motion diagrams, which car is going slower. So that begs the question, well, what is the motion diagram? We have a car that each subsequent image of the same car is its position at equal time intervals later. And so the one on the right in those equal time intervals as the one on the left, the position or the displacement between these is slower, or the displacement between these is less, and so the speed is obviously slower. And so speed on the one on the right is faster because the displacement, that's the key, the displacement is more in the same time intervals. Okay, that's part of the assumption of the problem, is that each of these are equal timestamps. And so the smaller displacement means smaller average velocity. So again, that's what the motion diagram was. Hopefully these quick check questions will be helpful for you in live, or if you're watching it recorded. Okay, and then we also quickly reviewed the particle model about how we can more or less treat most objects for the first 11 or so chapters as just being dots. The shape doesn't really affect the motion. We're not considering the shape yet. Very few instances in which we do. Drag, rotating objects, waves, that where the motion does affect it, but that's another example. And here we go. Here's another quick check question. If you're watching this recorded, you can certainly pause it and contemplate to yourself. But what we did was look at these three motion diagrams without velocities, just positions, and even no coordinate systems. So the first one, the dots are getting spaced further and further apart in time. So the thing is increasing speed downward. So this is like you throw a basketball, from a second floor of a building and it squashes towards the ground. So part B is in time, the distance between the dots is the same. So that means the displacement is constant for each of those time intervals. So there's an object slowly settling to the ground, like a dust particle or something. And then the one that we don't really see that often, part C, would be we're at high speed moving downward and then slowing down. All right, this isn't like when like an egg splats onto the ground. This would be like your parachute opening for a skydiver, or they might have like a planet or a satellite or whatever making a descent onto Mars. This is like the 7 minutes of terror that NASA talked about several years ago when they were launching Curiosity to Mars, which, think about, it's fascinating that we're doing that, sending, robots to other planets. It's really neat. But yeah, this would be decreasing speed while moving downward. Another more everyday example, now that I think about it, would be problem C would be, like you're going down towards, like you're moving down in the elevator towards the first floor, right? And then, so you're moving down, and then as you approach the floor, as you approach the first floor, your speed decreases to zero. So certainly that's how you match up those questions. We also talked about vector addition and vector subtraction. So position is our first quote unquote vector quantity, right? It's a how much and a in what direction. And so that's really what the dots are in the motion diagram. The dots are shorthand for these position vectors that all start from the origin of a coordinate system. And then everybody disagrees on what the position of an object is because everybody's got their own coordinate system. And yet, provided that all these coordinate systems are at rest, everybody agrees on the displacement of the object. Because the difference between each of those position vectors is the same for every person in their coordinate system. So displacement is our first major physical quantity that we define. And to be completely honest, it's the quantity on which pretty much all the other quantities, at least in these first several chapters, are based on. That and mass, we'll need mass and time. So of course we have a little tactics box for summarizing how you do the tip to tail method of the vectors, adding vectors. Again, this is more detail in the YouTube video. And then, so here's one quick check question. How to add P and Q. Well, if we go to the annotate button, let's see, there we go. All right, let's just apply the classic tip to tail method. So we start off with P. Draw P like that, next to it, vector P. Okay, and so what's the tip to tail method? We take vector Q. What I'm doing right now is I'm like kind of outlining it sort of with my fingers to see about how big it's going to be. And then place the tail of Q on the tip of P. Since this is like our first try, I mean, these aren't meant to be exact, but oops, not minus Q. This is going to be Q. And so when you arrange these vectors, tip to tail, tip to tail, tip to tail, then the resultant vector, when you complete the triangle, for if it's just 2, is the sum. And sure enough, the slides have the answer. I mean, they did exactly what I did up there. What about vector subtraction? Well, for vector subtraction, you have to introduce the opposite of a vector, which is just either way you want to say it. It's either for a vector in 2D, it's just rotated 180 degrees. But for vector in 3D, it's in higher dimensions, it's reflected about the origin. So every coordinate of the vector, every component of the vector, whatever that is inverted. And so you're adding the opposite of a vector. And certainly we give the instructions for that, for A minus B. You have to have the opposite of the vector. And so if we try this, same thing, we start off with the same P vector. Let's see, I'll put it down here. But now in looking at this Q vector, we have to take the opposite of it. We have to define the opposite before we jump in to add the opposite to P, and we'll bring that down and minus Q. So vector subtraction is nothing more than adding an opposite of a vector to the first vector. Sure enough, they do the same thing. But, you know, and that's a remark that I would make. Don't rely on all of these videos, all these PowerPoint slides. It's one thing to see something done. It's one thing to hear it done. But evidently, by the sense is that, you know, doing it with your hand, writing the stuff out is the best way to learn all this stuff. Not just doing it on listening or watching. Actively, like writing this stuff down is how you really learn it. Okay, and so another quick review, time interval, nothing much to say here, just, you know, everyone's going to agree on the same time interval in seconds. And then, so we define velocity from displacement and the time interval, right? And so we add velocity. So we include velocity vectors into the complete motion diagram by these, you know, by connecting the dots, pretty much. We're connecting the dots with these little arrows. Those arrows technically are displacement vectors because it's from one position to the next, but it's scaled by unit time, and it's a tool to help us understand. So it's technically displacement, but we're going to call it velocity, like displacement scaled by some unit time. Okay. And here's a quick example. And then acceleration vectors. Well, once we have a velocity vector, now we can imagine motion diagrams where the velocity vectors themselves change. And so that's how we define acceleration. And that's kind of the whole theme of this first chapter, kind of concepts of motion, is really for us to kind of get a feel about acceleration. I'll just tell you right now, when you accelerate, when you accelerate, you feel something different. You don't feel the acceleration. You feel some effect of you wanting to stay at rest. You feel an inertial effect, kind of. And so they show here how to calculate, or how to, this another tactics box, how to calculate a acceleration vector given the two velocity vectors. You have to do the same thing. You have to start with the two. Start with the two velocity vectors. Oh, okay, yeah, right. So you start at the very top. You start with v final. Is that what they have here? Oh, start with v final, v sub f, vector v sub f, and then add the opposite of v initial via tip to tail. So we're taking v final, adding the opposite of v initial, and then the resulting vector, obviously it's down there, but the resulting vector, this is not acceleration right here. This vector that I just drew is not acceleration. That is the change in velocity vector. It is not the acceleration vector because you're just subtracting. Acceleration is not a difference of velocity vectors. It is the difference in velocity vectors multiplied by 1 over the time interval. And sure enough, we go to the next slide. Oops. Yeah, we go to the next slide. Yeah, we'll see on the bottom or at the top here what I just drew, that v sub 0, or that's delta v. And then so we observe that acceleration is in the same direction as delta v, and we just add it, in that same direction. So these acceleration vectors will always be opposite, or the acceleration vectors in these motion diagrams are always on the above or next to the dots that are between changing velocities. And that's evidence. Oh, we have a quick check question. Okay, and so in looking at this question, we have to think backwards of what we had just been doing in that tactics box. And so there's a couple of these choices that can get a little muddy, even though, it's only the first chapter. So what does acceleration mean? Okay, if we're moving down and we're accelerating up, that means our change in velocity. So v2, okay, so if we're going to write v2, that equals, it technically equals our first velocity plus the change. I don't like that plus sign. So first velocity plus our change. Okay, and now we just have to remember that the change in velocity is proportional to, I don't want to be too careful, but technically, well, so basically the change in velocity vector is proportional to the acceleration vector. They're both in the same direction. And so that means that the change in velocity will also point up. So that's just going to make this one smaller. So this is v2 vector, and then it ends up at point 3. Okay. Let's see. Yeah, and so I'm looking at this. Certainly we have the answer being B. Did they do the same thing, sort of? Oh, they have it. Okay. Right. So what are some of the other choices, right? A would be an acceleration that pointed downward. And then C would be somehow thinking that the acceleration instantly makes the motion stop. And then D, sometimes people think D, the acceleration doesn't automatically make the particle change direction. And certainly all the more so for folks that may have thought E. You know, if you like bounce a ball on the floor, then certainly like, just do that real quick. If you bounce a ball on a floor here, it's moving downward for the initial piece of I. It's going to have a huge acceleration upward. Okay, and the reason is that the acceleration is going to be so big that you're not going to have time to look at the change in velocity in the time interval. It's just the change is going to be so rapid. That's what we mean by a large acceleration. But if it falls down with the speed of, say, 5 meters per second, and it bounces up with the speed of, say, like plus 4 meters per second, you can be sure that it reaches every speed in between there as it goes. But it's not always, you can't always measure that, because physics is a measurement science. It depends on, it depends on what you measure to depend if it instantly changes direction or not. Okay, so I'll let you read this about what makes a complete motion diagram. It needs a coordinate system, needs the dots for the position, needs the arrows connecting the dots for velocity, and then it needs the acceleration if those velocities change. And this is a perfect example, like I mentioned in the lecture videos. The important thing that I wanted to mention for this discussion today was these signs of acceleration. We actually have, so what does it mean for speeding up or slowing down? So evidently an object that is slowing down is accelerating opposite to its motion. Now think about that. When you're driving and the light turns red and you stop, okay, you're moving forward, but you're accelerating backwards. It's kind of weird to think that you're accelerating backwards while you're moving forward. And what causes even more confusion is that what happens to you? Well, as you slam on the brakes, you feel flung forward, actually. You and the car are moving forward, you feel flung forward, and yet you're accelerating backwards. So that's what's kind of weird about acceleration, is that decreasing speed always means you're accelerating backwards to your motion. Going back to the elevator example, when you're descending to the bottom floor of a building, once you hit that bottom floor, right, you're moving down, but you're accelerating up as you're moving down. And so acceleration, when you decrease speed, you're always accelerating opposite your direction of motion. And it gets even more hairy when you're moving in 2 dimensions. Like if you're, once again, at a traffic stop and you're in the turning lane and you see the green arrow to turn left and you're like trying to make it before the yellow arrow and then the red light, right? Let's say you take the turn to make that left turn. What do you feel? You feel flung outward towards the passenger side of your car, and yet you're accelerating towards the driver's side of the car. And in that case, your acceleration isn't even you're moving forward in the turning car, and yet you're accelerating horizontally. So but you feel pushed out horizontally the other way. And so it's pretty interesting. And this is why we do this chapter, to try and separate our notions about, velocity and acceleration and position. So let's do another quick check question. So in this example, in this quick check question, cyclist is starting at 20 miles per hour. All of them are to the right, and ends at 15 miles per hour. But he comes to a halt in between that time. Okay, so 20 miles per hour to a stop, and then picking back up the pace for 15 miles an hour. Maybe they're at a stop sign or something. So just looking at the velocity vectors, you can immediately eliminate a couple of ones, because if you look at C, you start off with a small vector and end with a large vector. All the other ones, you start with a large vector, velocity vector, and then shrink to 0 and then extend to a smaller vector. So C can be eliminated by just looking at the velocity vectors. Now, look at A. Look at the acceleration vectors for A in the first half. The velocity is decreasing, and yet the acceleration is in the same direction as the velocity. Okay, an object is increasing speed when its velocity vector and acceleration vector are in the same direction. So this doesn't make sense because the speed isn't increasing. And it doesn't make sense on the second half either, because we're increasing our speed to the right, and yet we're accelerating backwards. So again, that doesn't make sense. Looks to me like some people believe in choice A that acceleration is always towards the 0 or something like that. That's all I can think of. Of course, B is the one. Let's see. So B, large vectors, large velocities decrease to 0. Right, from a backwards acceleration, and then a positive acceleration increases the speed in this case. So certainly it is. Certainly the choice is B. What about choice D? A couple people chose D. D suffers from the same error in the acceleration in the beginning. It's got the correct acceleration after it comes to stop, however. All right, so as we keep going, one thing I mentioned in the videos is that the signs of acceleration is really important. And so we should go through some of these examples. Again, what does it mean for the acceleration or what does it mean for the position to be positive? It's just to the right of the origin or up if we're dealing with a vertical coordinate system. And then down and to the left means negative. Now, so what does it mean for a velocity to be positive? Again, this is just 1D, so velocity vectors have a plus and a minus. That just means you're moving to the right. That's it. It means that your displacement vector points to the right. And then if your displacement vector points to the left, then your velocity is negative. Now, what about acceleration? What does it mean for an object to have a positive acceleration? This is where people get into the mistake of thinking that this is speeding up, that positive acceleration equals speeding up. Okay, that is wrong, because a positive acceleration means that you're accelerating to the right. I mean, it doesn't have enough information by itself to tell you what's going on with the motion. You need to know what else is happening. So really the takeaway is that a rightward acceleration could mean increased speed to the right, or decreasing speed to the left. And the fact that it could mean either of those, that's what a positive acceleration means in the x direction. If it's negative, then you flip those increasing and decreasing. So negative acceleration could mean that you're either increasing speed while moving left or slowing down to the right. Now, speeding up and slowing down are not good words when we're talking about vertical motion. So that's why I stick with increasing speed. Okay, so same thing here. Let's see, it looks like we had another quick check question. So this question has to do with turning points. whether or not an object is accelerating when it changes direction or when it turns around. And the answer is absolutely, it's still accelerating, because it was moving up and then it was at rest and then it was moving down. So what would that look like with the motion diagrams? Okay, it means basically you start off, you're moving up. Let's see, so you need at least like 3 spots. So you're moving up, that's 1. Here we go. Yeah, and then 2, you're at rest, and then 3, you go back down. Okay, so the upward is the initial velocity and the downward is the final velocity. So the delta V then would be final velocity, V final, minus initial velocity. And so it points downward. So delta V points downward, and you have, in that turning point, you have a downward acceleration. Okay, so just because we're at our highest point in the air doesn't mean that our acceleration changes. Here's another thing that gets people tripped up. Well, you kind of need the graphs for it, but a lot of people think that when we're accelerating, so you throw a ball up into the air, that the acceleration versus time graph would be negative, and then jump up to positive once it's now going down. That means, once again, that's the feeling that you think acceleration negative means slowing down, and that's a Y subscript, and that positive means speeding up. And that's not necessarily the case. When you throw a ball up into the air, it's actually always negative. It's negative when it's going slowing while moving up, slowing up. It's negative when it's turning around, and it's negative when it's speeding up, speeding downwards, increasing speed downward. So that's very important to keep in mind. Certainly glad that I asked that quick check question. Okay. Certainly still points down, even though, and they have a little cartoon here. I like mine better, but certainly theirs is more detailed. Anyway, so any more clicker questions? Yeah, we got another one here. So as we're looking at this quick check question, what is the sign of position? Well, even though we're moving to the left, we're still to the right of the origin. Oops. And even though since we're to the right, oops, sorry, wonky. Since we're to the right of the origin, that means our position is always positive. Okay, so our position is always positive. Our velocity, since we're moving to the left, certainly has to be negative. Oops. Our v sub x has to be less than 0 since we're moving to the left, even though we're to the right of the origin. Okay, and since we're decreasing speed, means that we're accelerating to the right. Our acceleration is opposite. The ant that is slowing down right here is accelerating to the right, even though it's moving to the left. And so in looking at our choices here, position is positive, velocity is negative. So yeah, it would certainly be B. So for folks that chose choice A, the speed is positive, but speed's a magnitude. It's always non-negative. Okay, so it's just flipping each of these signs. Yeah, so you just have to know what those signs mean. Good, and then it looks like we have, oh, these are really helpful to ask, actually. Is it asking for the sign of acceleration? Oh, and I just did it. I gave away the answer, as usual. Acceleration is positive, right? Because it is, it's decreasing speed, and yet it has a positive acceleration. So the signs of these problems are really important, and they will also affect what the graphs look like. And so with the last couple minutes, let's go through this motion diagram and try and understand what the graphs of position, velocity, and acceleration look like. And we'll do a lot more of this and also in the coming problems as well. Let me switch to my whiteboard real quick with the couple minutes we have left. Okay, so now how you write these graphs are you start off with the position graph at the top. Okay, so x versus t is at the top, and then velocity is in the middle. And then acceleration is at the bottom. We do this to stress the integro-derivative nature of these three quantities. And you always start at acceleration. Acceleration is the best one to start off with. As it's slow, it's always strictly positive. Okay, so this will be like t final when it comes to rest. What is the velocity vector look like? Well, it's negative because we're moving to the left, but it's approaching zero. So, and this is the same t final. It actually has a positive slope to zero. Again, this is for the graph of the cart or whatever that's slowing down towards the origin. Okay, so it's moving to the left, but slowing, and so I know those arrows don't look very good. It's moving to the left and slowing, so it's got a large leftward velocity that's getting smaller and approaching zero. And then finally, what does the position graph look like? Well, you never give yourself enough space when you're drawing these things, so I'm not going to bother deleting the x, but it's a parabola, okay? And actually, that x is kind of in my way. Let's see, so I'm going to get rid of it and then quickly go back to my pen. Really quick. Oh, sorry. Okay, there we go. Okay, so you start off with a large, so you're positive, but you start off with a large negative slope. And that negative slope, it's getting less slopey. Right? The slope is getting smaller and it approaches zero because, yeah, so these dashed lines represent the slope of the position graph, but that is the values of the velocity graph that are getting smaller. And sure enough, the slope of this line, right? Slope of this line is the number right here. The number. So if this is like 2, so this, if it's like 2 meters per second squared, then the slope of the line is 2 meters per second squared. And the slope of the tangent line for the curve in position, that slope is getting less and less steep until it, at the very end, approaches zero, actually at the origin. So that's another thing that's confusing, is that the slope of the position graph is zero and the position is also zero. Too many zeros in a problem confuse folks, but that is how these graphs are related to each other. And for all of your homeworks for chapter 2 that are due next week, I would strongly encourage you to draw a position, velocity, and acceleration graph for each one of those problems. Because we'll get into examples where there's multiple like changes in the acceleration and so on. All right, so this concludes this lecture. In the next lecture, we'll be talking about, well, we'll start chapter 2 pretty much. There's a few more things in the videos to watch on units and sig figs. You can certainly pick that stuff up on the videos, but I want to jump into chapter 2 next time.